بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. المحاضرة دي بتتكلم عن الانرجي سبلاي اوف ذا هارت. هم اكشولي المحاضرتين ارتكل 1 و 2 هيتشرحوا من خلال this one presentation. At the beginning, we're going to read this clinical case scenario. It's very important. We're going to focus on certain important keywords and information which will help us to understand the lecture. This case is in the form of a 73-year-old female, has shortness of breath when lying down. She has found that using a couple of pillows at night makes it easier to breathe. يعني الحالة عندنا هي عبارة عن an old female عندها صعوبة في التنفس بالذات لما تبقى نايمة على ظهرها وبتحتاج تنام على عدد من المخدات العالية عشان تقدر تتنفس بسهولة. The past medical history of this female is that she was diagnosed about 7 years ago by to be hypertensive and she's already receiving antihypertensive treatment. On examination, bilateral basic palpitations was here and a lateral displayed apical impulse. Echo examination اللي هو سونار على القلب لقى ان في dilated and moderately impaired left ventricular contraction which is characteristic of heart failure. يعني الحالة عندنا داخلة في heart failure سواء كان السيمبتومز الباست هيستوري الاكزامينيشن الاكو كله رايح في اتجاه ان هي عندها a sort of heart failure. عملت NMR spectroscopy nuclear magnetic resonance spectroscopy. الانفستيجيشن ده is not a routine one بمعنى ان ما بيطلبش مش اي عيان عنده مشكله في الهارت او هايبرتنسيف هيطلب الكارديولوجيست هيطلب منه التحليل ده او الانفستيجيشن ده، لكن احنا عاملينه او طالبينه want to explore the cause inside the heart which could be leading to heart failure. وفعلا results or findings showed decreased phosphocreatine and ATP in the heart. في two molecules حاجة اسمها phosphocreatine و ATP هنعرف بعد شوية ان الاثنين دولت عبارة عن energy representing the energy currency inside our body لأنهم إنهم declined or decreased inside the heart. The most important investigations, which is the lab investigation, the chemical lab tests, so showed that serum lactate is 2 to 4 millimole per liter. طبعا احنا هنقارن between the result والnormal reference range. طبعا هنلاقي ان السيروم لاكتيت عالي. لو بصينا على السيروم نيفا what's نيفا it is non-esterified fatty acids. طبعا كنا عارفين fatty acids in the serum بتبقى free fatty acids يعني مش عاملة ester bond مع glycerol يعني مش not in the form of triacyl glycerol ولا عاملة esterification مثلا مع الكوليسترول عاملة كوليسترول ester، لا هي free non-esterified in the serum. برضه لو قارنا ما بين level in the serum the serum the patient and the normal levels هنلاقيها عالية. As regards blood sugar, the serum glucose normal يعني بمعنى ان هي مش diabetic. Very important we found that the total cholesterol الكوليسترول عندها ايه رأيكم عالي. يبقى عندنا حاجتين عاليين اللاكتيت عالي النيفا عالية الفاتي اسيد والتوتال كوليسترول عالي. As regards treatment الكارديولوجيست اداها طبعا الستاندرد ثيرابي العادي واداها كمان a certain metabolic agent وشرح لها قال لها ان الميتابوليك agent ده اللي هزوده لك الدواء ده هيبدأ يحسن الميتابوليزم and improve the cardiac metabolism and improve its energetic status. ده كانت الكيس بتاعتنا. هنبدأ نعمل ايه نفتكر مع بعض حاجات مهمة. اول حاجة هنفتكرها اللي هو البيشنت كومبلين. مين فاكر البيشنت كومبلين اللي كانت بتشتكي من ايه؟ صحيح هنلاقي البيشنت كومبلين shortness of breath when lying down لدرجة إن هي تحتاج a couple of pills that might make it easier to breathe. ده البيشنت. طب نفتكر مع بعض الانفستيجيشنز. ايه الابنورمال investigations finding in this patient؟ فاكرين الانفستيجيشنز اللي عملتها؟ الايكو، ايه رايكم في الايكو؟ صحيح. الايكو showed dilated and moderately impaired left ventricular contraction characteristic of heart failure. بقية الانفستيجيشنز كده عملت some laboratory investigations. هنفتكر مع بعض. صحيح، كان في high serum نيفا، high serum lactate، high cholesterol، وكان inside the heart كان ال ATP والفوسفوكرياتين كانوا low. هنبدأ نعمل case analysis، بمعنى ان احنا هنبدأ نطرح بعض الأسئلة وهنشرح بحيث ان احنا من خلال الشرح هنوصل للإجابات الصحيحة للأسئلة دي، وبالتالي هنكون حققنا intending learning outcomes or objectives of this lecture. أول سؤال: is there a relation between cardiac energy production اللي هو ال ATP والheart failure؟ السؤال الثاني: ايه هي الفولز of a normal heart in different physiological conditions؟ طيب how fools are selected by the heart and what regulates the selection and so on. The other questions: what is the metabolic profile in heart failure? How ATP production is affected? فكان في fatty acid واللاكتيت كانوا increase، طب why؟ وهكذا. هنبدأ بأول سؤال: is there a relation between cardiac energy production ATP and heart failure؟ علشان نجاوب السؤال ده لازم طبعا تبقى عارفين المعلومة دي وكلنا عارفينها، ان الهارت is one of the most active tissues in the body. والريليشن بين ال ATP وحدوث الهارت فيلير او عدم حدوثه تكمن الإجابة في كلمة equilibrium. There must be a fine equilibrium. يبقى الميوكارديال function depends on a fine equilibrium between إيه بقى؟ between the cardiac work and of course this cardiac work is to meet the body requirements and the energy in the form of ATP. So I have to have an equilibrium between the energy and the cardiac work. If there is impaired substrate metabolism, this will contribute to decreased ATP production. This will lead to defective contraction or contractile dysfunction in cases of heart failure, as you see in the slide. So, decreased ATP production as a result of impaired substrate metabolism will contribute to contractile dysfunction in cases of heart failure. So ATP is very, very important to the heart. So we want to speak about how ATP is generated. Before going through details, we have to highlight on this important fact that heart is a highly oxidative tissue, which means it depends upon oxygen in its metabolism. So ATP to be generated in heart, it is through oxidation process. 95% of ATP produced inside the heart is from oxidative phosphorylation. So large amount of ATP is produced or generated by oxidative phosphorylation, of course, to support the high rate of cardiac power. This occurs under normal, basal, non-ischemic conditions. 95% or even more of ATP is generated or comes from oxidative phosphorylation. Where does it occur? Inside the mitochondria through the electron transport chain. You took details of this electron transport chain in the respiratory module. The remaining 5% will be produced through or derived from substrate level phosphorylation. What is the meaning of substrate level phosphorylation? Are certain chemical reactions which produce ATP or GTP immediately مباشرة. This occurs through glycolysis and citric acid cycle. They give us ATP at the substrate level phosphorylation. Okay. من رحمة ربنا بينا إن إحنا ما بنستخدمش كل الطاقة أو كل الأكسيديف كاباسيتي بتاعتنا in normal conditions. At rest وإحنا مريحين. At rest when the heart is not under extra work, only 15 to 25% of its maximum oxidative capacity will be consumed, reserving about 80 to 90% of this oxidative capacity of the mitochondrial electron transport chain will be used in situations of maximal cardiac work. The heart uses about 60 to 70% of the generated ATP for its work to full contraction, and 30 to 40% is important for ion pumps to maintain ion homeostasis, especially that of the calcium ATPase in the sarcoplasmic reticulum. This figure shows that in the presence of oxygen, again, heart is a highly oxidative tissue. In the presence of oxygen, through the electron transport chain, I will generate ATP. What are the fuels? I've got fatty acid, glucose, lactate, whatever. These are the fuels of the heart. On oxidation of these fuels, I will get reduced coenzyme NADH. This reduced electron carrier will enter through the electron transport chain and change ADP to ATP in a reaction of oxidative phosphorylation. You took it in details in the respiratory module to generate ATP. This ATP, 60 to 70% is used for contraction. The rest is for ion homeostasis. Okay, now we're going to speak about the ATP pool inside the heart. As we mentioned, ATP is very important for the heart. It's a highly oxidative tissue. So I suppose that we've got very large amounts of ATP inside the heart, that my ATP pool is very high. This is not actually the condition. If we measured the ATP at any second, we found that the heart has a relatively low ATP content. Why? Because it has a high rate of ATP hydrolysis. That means I've got almost a complete turnover of the myocardial ATP pool approximately every 10 seconds. This occurs under normal conditions. So I have a relatively low ATP, around 5 micromole per gram of what weight, because they are hydrolyzed every second. I've got another energetic molecule called creatine phosphate. It is relatively higher than ATP, about 8 micromole per gram wet weight. What is creatine phosphate? Actually, creatine phosphate, it serves as an ATP transport system. This phosphocreatine, in comparison to ATP, is a small molecule. As regards its size, it is a small molecule which can diffuse through the mitochondrial membrane. So inside the mitochondria, where I have the respiratory chain or the electron transport chain, where oxidative phosphorylation occurs, changing ADP to ATP, I've got an intramitochondrial enzyme called mitochondrial creatine kinase. It will take the phosphate from ATP, add it to a creatine molecule to have phosphocreatine, which will be easily diffused through the mitochondrial membrane into the cytosol, because it is smaller molecular weight, has a smaller molecular weight than ATP. Hence, it can be used to generate ATP in the sarcoplasm by the presence of another enzyme, which is cytoplasmic creatine kinase. This cytoplasmic creatine kinase will again extract this phosphate from phosphocreatine, put it on ADP, so I will have one molecule of ATP in the cytoplasm, and phosphocreatine will return again to creatine, diffuse through the membrane, enter the mitochondria to carry another phosphate group from ATP by creatine kinase inside the mitochondria to become phosphocreatine, diffuse outside by cytoplasmic creatine kinase. ADP will take this phosphate to it. I will have ATP, heart will use it for contraction, and again creatine will be reused. So this shows that ATP, the creatine phosphate, serves as an ATP transport. Okay, then what are the substrates or fuels of metabolism in a normal heart? In other words, the same question could be, what are the substrates for oxidative generation of ATP of a normal heart? I've got 4 main substrates: fatty acids, glucose, lactate, ketone bodies. Actually, you'll notice that I'm putting them in a certain order. So this means that fatty acid is the major substrate or fuel for the heart. وطبعا ده من رحمة ربنا ان في حاجة اسمها metabolic flexibility. يعني مش هقول لك ان الهارت بيعتمد بس على الجلوكوز، لو مفيش جلوكوز الهارت هيقف، او كيتون بوديز او فاتي اسيد. لا، لو مفيش فاتي اسيد طب هنروح للجلوكوز، طب جلوكوز طب في starvation هناخد كيتون بوديز. So there are metabolic flexibility to meet energy demands through rapid changes in fuel utilization. استخدم ده، الكونديشن اتغير استخدم ده، رجع تاني استخدم ده، لا بقيتش under severe exercise اخد الكيتون بوديز. So and this switch from one fuel to another is under hormonal regulation and substrate availability effect. Again, these are the fuels under basal condition of cardiac metabolism. Fatty acids is the major substrate, 60 to 80% of substrates which are contributing to produce ATP upon oxidation is fatty acids. The rest, 20 to 40%, are actually coming from glucose, which could be glycogen or glucose itself or lactate. They represent the 20 to 40% of all the substrates of metabolism of the normal heart under basal condition. Again, this is a very important information. Fatty acid oxidation represents the major source of energy for myocardium, up to 80%. Glucose metabolism, glucose, glycogen, lactate, provides the remaining quantity of energy. Okay. Now we're going to speak about lactate. A carbohydrate in general is an energy source for cardiac muscle. We start by lactate. Lactate will be extracted from blood from producers. These producers, you can try to remember what are the producers of lactate. Yes, I've got RBCs. Do you remember the anaerobic glycolysis, which the end product will be lactate in RBCs, as well as contracting skeletal muscles? These are 2 producers of lactate. The consumers, as we just mentioned, heart, oxidation to give us ATP, and then I've got liver and kidney. They will use lactate to produce glucose in a process called gluconeogenesis. Now we're going to explain the lactate metabolism in the normal heart cell in details. Lactate will be extracted from blood, mostly from, yes, contracting skeletal muscle and RBCs. It will enter through the myocardial cell. Then lactate will be changed into pyruvate. By which enzyme do you remember? Yes, lactate dehydrogenase changed lactate into pyruvate. Notice that pyruvate inside the myocardial cell will be derived approximately equal proportions from lactate by lactate dehydrogenase and from glycolysis. Okay, from cellular lactate, from the blood lactate, and from glycolysis inside the myocardial cell. So I got now pyruvate inside the mitochondria. It entered the mitochondria. I got the pyruvate dehydrogenase complex. Do you remember this reaction, which is an oxidative decarboxylation reaction, which will change pyruvate into acetyl-CoA. Then acetyl-CoA together with oxaloacetate will form what is called citric acid cycle to enter the TCA-Krebs cycle or enter the TCA cycle. So the citric acid cycle in mitochondria will be filled for both acetyl-CoA and oxaloacetate for complete oxidation. This reaction of pyruvate dehydrogenase, as we said, it will give me acetyl-CoA and will give me NADH plus H. Both the products of TCA, NADH plus H, FADH2, will go through the electron transport chain in the presence of oxygen. Very important. We need to have oxygen. Oxygen will change to water and ADP into ATP, an oxidative phosphorylation reaction. So I will have ATP from lactate. Again, contractile skeletal muscle and RBCs are the source of lactate in blood. Lactate will enter the myocardial cell by lactate dehydrogenase. Lactate will be changed into pyruvate, which will enter the mitochondria. By the pyruvate dehydrogenase complex, pyruvate will be changed into acetyl-CoA. Acetyl-CoA with another molecule of oxaloacetate will form citric acid, which will go through the citric acid cycle or the Krebs cycle, the TCA cycle, for complete oxidation of glucose. Then, this reaction will give me NADH plus H to the electron transport chain, and the products of the Krebs cycle to the electron transport chain all will be the source of ATP inside the heart. Now we're going to speak about glucose as a fuel. Glucose in blood will be entering the myocardial cell, be transported from blood into the cardiomyocyte through certain glucose transporters, glucose transporter 4 mainly, and to lesser extent glucose transport 1. It will enter the myocardial cell. Okay. Another source of glucose is glycogen. Glycogen stored inside the myocardial cell. But actually, the cardiac glycogen is very small, about 30, I think, millimole per gram weight compared to the huge amount, about 150 in muscles, for example. So, I will have glucose inside the myocardial cell entering from blood. Glucose will enter, or from the glycogen, cardiac glycogen pool or store. I have glucose phosphate. It will go through glycolysis to give me pyruvate. And pyruvate will enter the mitochondria. Again, say it with me, pyruvate dehydrogenase will give me acetyl-CoA, acetyl-CoA. This occurs in the mitochondria when pyruvate is decarboxylated and oxidized into acetyl-CoA. This pyruvate as well could be carboxylated into oxaloacetate by the enzyme called pyruvate carboxylase. So pyruvate, it could be decarboxylated and oxidized to acetyl-CoA by pyruvate dehydrogenase complex, or it could be carboxylated into oxaloacetate by pyruvate carboxylase. Both acetyl-CoA and oxaloacetate will be condensed together to form citric acid, the TCA. I got NADH plus H from this reaction. They will go through the electron transport chain to give me ATP. Okay. Now we're going, don't forget that if I have complete oxidation of one molecule of glucose, I will have 36 to 38 ATP will be produced from one molecule of glucose. Okay, now we're going to speak about free fatty acids as an energy source for cardiac muscle. Don't forget, as we mentioned before, free fatty acids is the major source of energy for the heart. Up to 80%. Free fatty acid is the major source. Free fatty acid as palmitic acid is a major source of energy. Okay. The rate of fatty acid uptake by the heart is primarily determined by its concentration as free fatty acid in plasma. We know that free fatty acids comes from breakdown of triglyceride in fat cells, especially under conditions of stress, metabolic stress. If I got myocardial ischemia, severe exercise, fasting, starvation, all these are stress, will lead to lipolysis, activating of the hormone-sensitive lipase to break down TAG, which is stored in adipose tissue, to give me free fatty acids. Okay, these free fatty acids will enter the cardiomyocytes by passive diffusion. Or I've got another mechanism, which is protein-mediated transport across the sarcolemma. Free fatty acid will enter inside the myocardial cell. Another source of free fatty acid, not only that in blood, I got another source inside my myocardial cell, which is the TAG pool. I got triacylglycerol pool inside my cell, as well as the TAG present in all over the body in adipose tissue. So I will have lipolysis of the TAG pool by the enzyme called hormone-sensitive lipase. And as we said, in cases of metabolic stress, physical exercise, fasting, myocardial ischemia, catecholamines will be released, which will activate the hormone-sensitive lipase inside the myocardial cell, and the hormone-sensitive lipase, which is present in intracellular, in adipose tissue, in all fat cells all over the body, will release free fatty acids in the blood or inside the myocardial cell. For this free fatty acid, whether coming from blood or which is coming from TAG of adipose tissue or from the TAG pool inside the myocardial cell, to be actually a source of energy, or to be ready for oxidation, it should be activated. This free fatty acid will before undergoing beta oxidation, it should be activated into acyl-CoA. This is a very high energy consuming reaction. I've got ATP, one molecule, if we will change into AMP, so I will extract two high energy from this ATP in the presence of the enzyme which will catalyze this reaction. Acyl-CoA synthase will change free fatty acid into acyl-CoA. This acyl-CoA, part of it will be re-esterified again to form TAG, about 30%, and the rest, 70%, will enter inside the mitochondria. We all know that this will need a certain transport system, which is carnitine acyltransferase 1, carnitine acyltransferase 2. These two enzymes transport acyl-CoA because this mitochondrial membrane is impermeable to acyl-CoA. So it will need this transport system, so it will enter inside the mitochondria. Acyl-CoA needs Cat1 and 2 to enter inside the mitochondria to undergo beta oxidation. Okay, so this is very important. You took it, I think, in the locomotor module. Or still you didn't take it, but you have to know that there is a transport system called carnitine acyltransferase 1, which will change this acyl-CoA to acylcarnitine by Cat1 to cross the mitochondrial membrane and then regenerate the acyl-CoA by acyl-CoA by carnitine acyltransferase 2 to regenerate acyl-CoA. Again, we need carnitine acyltransferase 2. Then, this single fatty acid will undergo, suppose it's palmitic acid, which is 16 carbons, for example. It will be broken by beta oxidation into 8 acetyl-CoA. Then these acetyl-CoA will enter, of course, the Krebs cycle. So beta oxidation will change acyl-CoA, break it down into acetyl-CoAs, and it will give NADH and FADH2. Acetyl-CoA with oxaloacetate will go through the TCA cycle. NADH and FADH2 with the products of TCA, which is NAD again, H and FADH2, all will go to the electron transport chain. Oxygen, we need oxygen, which will change to water, ATP into ATP, and we will have ATP, which will be a huge amount of ATP from one single free fatty acid. This will give us about 129 ATP. We want to compare between the ATP from one molecule of glucose, which was 36 or 38, and one molecule of free fatty acid will give me 129 ATP. You took the beta oxidation in details. Before, I think in the locomotor module, because I will have 8, if I'm starting by palmitic acid, 16 carbon, I will have 8 acetyl-CoA, I multiplied them by 12, plus I will have 7 times 5 ATP, 3 from each NAD and 2 from FAD, so I will have 7 times 5 because I will have 7 cycles of beta oxidation. Then I will subtract the 2 ATPs used in this activation. So the net, I will not ask you about the details of calculation of this energy, but what I want you to know that one single free fatty acid will give me a net of 129 ATP through the electron transport chain. Now is the turn of ketone bodies. Ketone bodies will be formed inside the liver in a process called ketogenesis. What is very important to know that the heart depends upon ketone bodies in conditions of starvation, severe uncontrolled diabetes mellitus, and severe exercise. Because all these conditions, in these conditions we have increase in fatty acid oxidation, which will give me very high amount of acetyl-CoA, which will go through building or synthesizing ketone bodies, which are water soluble in blood. So I've got acetoacetate or its reduced form. These are the ketone bodies which are present in blood, coming from liver. Synthesizing ketone bodies is a process called ketogenesis. So I'm synthesizing ketone bodies in conditions of starvation, severe exercise, uncontrolled diabetes mellitus. Why these 3 conditions? Because in these three conditions, I will have high fatty acid lipolysis. First, I will have high lipolysis because why lipolysis? I will be having high, it is a stressful condition, so high catecholamines, which will stimulate lipolysis. Lipolysis occurs as a result of activation of hormone-sensitive lipase. So catecholamines will stimulate the hormone-sensitive lipase. Hormone-sensitive lipase will start lipolysis, breaking down the tag into free fatty acids. So I will have a huge amount of free fatty acids inside the blood. These free fatty acids will undergo fatty acid oxidation, giving me huge amount of acetyl-CoA, which will be directed towards synthesizing ketone bodies, which are water soluble in blood. So I will have As a result of ketogenesis, a huge amount of acetoacetate or beta hydroxybutyrate inside my blood. They will be uptaken by the myocardial cell. They will enter the myocardial cell. Okay, when going through this myocardial cell, again will enter. Acetoacetate will go through the myocardial cell. It will be diffused through the mitochondria. In the mitochondria, it should be activated into acetoacetyl-CoA. So now it is active. Then I will break it down into 2-acetyl-CoA. This, what are we doing, is called ketolysis. I'm breaking down the ketone bodies, so it is ketolysis. So I have acetoacetate or 3-hydroxybutyrate, which are transported in the blood to the heart. In the heart, they will be converted to 2-acetyl-CoA. Who could complete? These 2-acetyl-CoA will be oxidized in the TCA cycle to produce energy, and this utilization of ketone bodies as a fuel is called ketolysis. This is called ketolysis, occurs inside the mitochondria. Ketogenesis only in the liver. It will be synthesized and used by the heart, ketolysis, to produce energy in case of starvation, diabetes mellitus, severe, uncontrolled, of course, and under severe exercise. Okay, now we are going through a very important part of this lecture, which is called substrate selection regulation. We've got fatty acids, we've got glucose, we've got lactate, we've got ketone bodies. All these, they serve as fuels for the heart, for cardiac metabolism, to produce ATP. How could the selection be regulated? Under the influence of hormonal regulation and allosteric regulation. So, substrate selection and use of the heart are modulated by allosteric or hormonal regulation. Of course, hormonal, I will have insulin and anti-insulin. Okay, insulin take the upper hand, of course, in the well-fed state. When you are eating well, you're in the well-fed state, insulin will be secreted from the pancreas. On the other hand, during starvation or in case of metabolic stress, severe exercise, fasting, I will have the anti-insulin, which are catecholamines. These are the two hormones. Let us look at insulin. Insulin, the well-fed state, will stimulate the glucose oxidation, but at the same time, it will inhibit fatty acid oxidation. On the other hand, on the other conditions, in the situations of stress, metabolic stress, I will have catecholamine, which will stimulate fatty acid oxidation and inhibit glucose oxidation. Okay, this is the hormonal regulation. Okay, allosteric regulation, it will be exerted on which reaction? Very important to know this information. It's an important information. We've got on the pyruvate dehydrogenase complex. Actually, the use of glucose or fatty acid and the switch in between both depends through allosteric regulation depends on the pyruvate dehydrogenase activity, because pyruvate dehydrogenase, as we know, this reaction changes pyruvate into acetyl-CoA and gives me NADH. You will notice that these are the same products of fatty acid oxidation. Again, fatty acid oxidation will give me acetyl-CoA and NADH plus H. So, pyruvate dehydrogenase will be inhibited by fatty acid oxidation. Why? Fatty acid oxidation is highly active, producing large amounts of acetyl-CoA and NADH. These are the product of this reaction. They will be accumulated in the cell, so I don't need this reaction anymore, so they will do allosteric feedback inhibition to pyruvate dehydrogenase. So this will stop the oxidation or complete oxidation of glucose, because pyruvate dehydrogenase to pyruvate by pyruvate dehydrogenase into acetyl-CoA to Krebs cycle to electron transport chain. If got fatty acid oxidation very active, so I will have plenty of acetyl-CoA NADH. It will block the pyruvate dehydrogenase activity, so glycolysis will end into pyruvate. This pyruvate cannot proceed to complete oxidation. This pyruvate couldn't be any more changed into acetyl-CoA. What does that mean? That means I'm going to explain something called glucose fatty acid cycle or Randle cycle. What is Randle cycle? Randle is the name of the scientist who explained this phenomena and explained how glucose and fatty acid metabolism are tightly linked and co-regulated. Fatty acids and glucose use by the heart is tightly linked and co-regulated. What does that mean? The use of one of them as a substrate will directly inhibit the use of the other. This is we call glucose fatty acid cycle. The use of fatty acid as a fuel will block the use of glucose. If I use glucose as a substrate, it will decrease the use of free fatty acids. Both of them are co-regulated or tightly linked together. This is what is Randle cycle said, and we have just explained it in the previous slide. Why? Let us go together through it. Free fatty acids entering the cell. I've got plenty of free fatty acids. Or from the tag pool, homosensitive lipase, free fatty acid will be activated by acyl-CoA synthetase using ATP to AMP acyl-CoA and enter the mitochondria. Okay, we explained this several times. This acyl-CoA entering the mitochondria will go through beta oxidation, will give me large amount of acetyl-CoA and NADH, which are the products of pyruvate dehydrogenase. If I'm starting by glucose, glucose will enter by glucose transporter 104 or from inside from glycogen. I've got glucose, glycolysis, pyruvate. Pyruvate enter the mitochondria, pyruvate dehydrogenase. So what I want to say that the primary physiological regulator of flux through pyruvate dehydrogenase and the rate of glucose oxidation is fatty acid beta oxidation. If fatty acid beta oxidation is very activated, highly activated, I will have plenty of acetyl-CoA and NADH, which are the products of this reaction, so it will stop this reaction by feedback inhibition, so pyruvate will not go through changing to acetyl-CoA. So I prevented the further oxidation of glucose through Krebs cycle through electron transport. Why? Because beta oxidation or fatty acid oxidation is taking the upper hand. If I wanted to inhibit fatty acid oxidation, so this as stop, I want to inhibit it. So I will have now decrease amount of acetyl-CoA, so there will be more and more increase in uptake of glucose and oxidation of glucose, and then